My name is Edoardo Giangrandi. I'm a second-year PhD student at the University of Coimbra, and I'm here today to talk about smoking gun signals from dark matter, and in order to shed light on the dark matter part through complex stars. Sorry for the bad pun, to shed light on the dark matter. It was intentional. So let's start with a review on the accretion part. And so as you can see here, as you can imagine, neutron stars are embedded in the galactic halo. And so we can imagine that there is already a mixture of baryonic matter and dark matter in the protocloud where these stars, the main sequence stars, are formed. And so from the very beginning of the star lifetime. Moreover, of course, we can imagine a main sequence star accretion, the creation of dark matter during the supernova events, and of course, any other accretion kind of scenarios like dark matter clumps or accretion of self-interacting dark matter. If you're curious about this last point of this list, check if Alexei talk tomorrow. In order to know more about the self-interacting dark matter accretion. So once we know that the dark matter is inside these neutron stars, we already know that we can form cores or cloud halos in neutron stars, but how can this dark matter affect the properties of neutron stars? So let's start with the easiest one, so MR curves. We know that from the Balik cluster, we have constraints on the cross-section between the dark matter and the normal matter, the baryonic matter. And so using these constraints, we can say with a good approximation that the baryonic matter and the dark matter are coupled just through gravity. And so we can split the TOV equation into two different equations, one for the dark matter and the other one for the baryonic matter. Here, just a bunch of definition of pressure, gravitational mass, etc. And one important parameter, actually, which is the dark matter fraction in our configuration, which is defined as the dark matter mass over the total mass of our system. So using this system of equations, the TOV equations, we can then obtain all the configurations for our neutron stars. In this case here, we are using a bosonic self-interacting dark matter model. I cannot go to details due to the time schedule. However, as you can see here, we have that both masses and radii are decreasing while increasing the fraction of the dark matter inside our configurations. Regardless of the baryonic equation of state, as you can see here, we are plotting different equations of state. Moreover, from the gravitational wave sector and the gravitational detection that we've been observed, we know that we can obtain some constraints on the tidal deformability. As you may know, due to the last talks, we have that this tidal deformability is highly dependent on the equation of state through T's Love's number, K2. And then here we need to take in consideration the outermost radius, because now we have two fluids, and so we have to be careful about which radius we should use in order to evaluate the tidal deformability and the total mass. So in a naive picture, in a simple picture, we can say that in a dark matter halo configuration, the outermost radius is the dark matter 1, leading to an increase of the lambda in our tidal deformability parameter. On the other hand, as you can see here, with the same parameter set of the previous plot for the MR curves, we have a dark matter core, and so the outermost radius coincides with the baryonic one, leading to more compact configurations, as I said before, and then with a decrease of the tidal deformability parameter, regardless still of the equation of state for the baryonic matter that we're using. In this case here, in order to evaluate the tidal deformability, we use an effective speed of sound approach. If you're curious, please ask. I don't have time. Moreover, another smoking gun signal from neutron stars is the thermal evolution. And so we do know that the contribution of neutrinos and photons, but we can have also an additional channel of heating or cooling due to the dark matter and the dark matter model that we are considering. For example, here I just mentioned axions, which could contribute to an additional channel for the cooling of neutron stars. So dark matter in a self-annihilating model can lead to heating or cooling. Moreover, here I would like to point out that also in the case of asymmetric dark matter, we have a modification of the cooling curves of our neutron star. Indeed, we can think about that as an additional fluid which has a gravitational pull on the baryonic matter, and so the density inside the inner regions of our neutron stars are increasing, and so this could trigger the direct Urca process and leading to a further channel of fast cooling, as you can see here. Moreover, last but not least, we have another smoking gun, and which we are trying now to split. We know that in dark matter, in neutron star configurations, we could also model the confinement phase transition to a quark-gluon plasma, as you can see here with the yellow curve. Here there is the onset of the confinement phase transition, and then we have the hybrid branch here in yellow. Here I just started playing with our naive and simple toy model where I fixed the mass of the dark matter particle and I changed the fraction inside. As you can see here, masses, tidal deformabilities, and radii are the difference between the two configurations. So the hybrid equation of state, the yellow one, and the dark matter mixed configurations are basically undistinguishable. So we need to split this degeneracy, and hoping with the future measurements of the neutron star's moment of inertia, we could potentially do something. Stay tuned for the paper, which is coming later this year. And here's the summary with all the smoking guns of dark matter in neutron stars, starting from the measurements of masses, radii, moment of inertia, with a few % accuracy from radio telescopes, space telescopes, and that are listed here. Moreover, what we can do is to perform numerical simulations of binary neutron star mergers in order to understand how we can detect this dark matter in binary neutron star mergers. And so we need, of course, computational time and, of course, good codes with a double two fluids approach, and everything should be fine, I hope. Moreover, we can also detect objects in contradiction with our understanding. For example, TS constraints that was just released last year with a super light, dark, baryonic, apparently, neutron star, or effects on the cooling or the pulse profile, light bending to the dark matter halo, and last but not least, this degeneracy between quark-gluon plasma, and so hybrid equation of state and dark matter cores. I'm running out of time, so sorry. Thank you.
We have time for a few questions. Back there.
Thank you very much. May I ask you to go on the one slide back, because I mean you were speaking to us. So,
yes, sorry.
Perhaps you said this, but I didn't get it. So you get this branch with the phase transition to quark matter, I guess, or something like this, and then you say that you can mimic the same MFR dependence with neutron stars with dark matter core. So can you a little bit elaborate on this? Because like if in GR, the moment when the stars reach one, I mean, it's not like the yellow and the black branch can coexist in GR. Like it's first the black branch, then it's the yellow. Wow. So can you elaborate more a little bit on that?
Yeah, sorry. So basically here we have the baryonic equation of state, which is the black solid line. And so there is no phase transition to a quark-gluon plasma, so no phase transition at all, or no dark matter. So that's the start of our model. Then we can use a phase transition to a quark-gluon plasma, but this is another one. So it's another equation of state based on the same baryonic matter. So basically here in this part, for example, we have the phase transition. So we have a quark-gluon plasma core, and then we have the baryonic envelope, let's say, all around the core. But these are two different models, and here in this lower part, we have just the baryonic matter in both cases, so but for both equations of state, since the onset of the phase transition is not triggered. Once this phase transition happens, then we have the yellow branch here, which is completely detached from the baryonic one, and we have the hybrid core, hybrid configuration, sorry, and then modifying all the parameters of our model, which in this case is the dark matter fraction and the mass, we can have a precise superposition of a dark matter, a mixed Newton star configuration with the hybrid equation of state. So in one case, we have a dark matter core in the interior of our Newton star, while on the other end, we have a Quark-gluon plasma core. And with these differences between the two different configurations, in this case, I chose 1.4 and 1.6 solar masses, we cannot distinguish by now, so far, the two configurations. So there is a degeneracy, and maybe it's going to be split at the moment of inertia. Let's see. I hope I explain a little bit better. Otherwise, thank you.
Go ahead. Right there.
So I have a question about the dark matter fraction. So is that an input in the calculation? Because it seems like a big number. So, or do you get it?
Yeah. This is a big number, but the problem, what I did in this case is that I fixed the mass of the dark matter to 2 GeV, and then I modified the fraction. But on the other hand, you could do potentially, I could do the same, fixing a dark matter fraction which is more feasible, let's say, so a 1%, let's say, and modify it and increasing than the mass of the dark matter particle. So in this case here, I could go for 5 GeV, for example, so increasing or 10 GeV, increasing the mass, lowering the fraction. And so
you mean like a 1% is feasible?
It depends on the accretion, but it depends on the accretion and how you can accumulate dark matter on top of a Newton star. You can go also for 0.5%, 0.3, depending on the model that you're using, you can have the same effects. And so in this case here, this is just a toy model in the sense that this one is a fermionic gas, and so basically there are no parameters apart from the mass. But modifying the model leading to more complex model of dark matter, then you can have more parameters to play with, and of course, then you can go towards lower fractions of dark matter, if this is your aim.
Okay, thanks.
One more question. Yeah,
Just to understand something. So in your model, dark matter and baryonic matter are just completely decoupled from each other? I mean, do they interact with each other at all? Is there any interaction among them?
Okay, so the only interaction that we are considering here is just the gravitational one. So they do interact gravitationally, but so far there is no interaction between the two fluids. So we have two fluids which are completely independent apart from the gravitational interaction between the two of them.
Okay, thanks.
Okay, I think we should move along and thank the speaker again.